Hi there. Today I'm going to talk to everyone about something that's very rarely talked about in high school calculus and pre-calculus and just basic math in general is calculating the arc length of a curve. So with calculus and just basic algebra, we can figure out that if we have, let's say, we have some curve here like this, right? We're looking at that curve from A to B, right? So that's our interval. We can figure out the slope of the tangent line at any point. We can figure out the area under this curve, right? We can figure out a bunch of things, but one thing that we haven't been able to figure out so far with what we learned is what the length of this curve actually is. So this interval right here, what's the length of that curve? If we were to take a string and cut it, how long would that string have to be to just span across this interval here? And even though it's not talked about very much, it's actually not a super hard calculation to do. It does involve some calculus. Okay, so let's say we had like, if we had a linear function, we wouldn't need calculus to figure this out, right? So if this was let's say y equals x, we could figure out this arc length from 0 to, let's call this a, right? We could figure out, this isn't, well, I guess it is an arc, but we could figure out this line length without really much calculus at all. Just we'd have to know this y, this x, and use our Pythagoras, right? So we'd have to do, we call this r squared, right, equals x squared plus y squared, blah, blah, blah. Add these two together, square root it, we'd get our r. And we can actually use the arc length formula for this question as well. Okay, so it can be applied to any function, f of x, or f of r, or whatever the function was, and we could get our arc length. So let's just kind of get into it. I'll show you what the equation actually is. So I'll just call it A for arc line. I'll call it L for arc length. It's going to be the integral from A to B, okay, of the square root of 1 plus dy by dx squared dx. Okay, what does this mean? Well, if we're trying to figure out the arc length of a curve from the interval A to B, so all that means is how long is the curve that kind of spans across those 2 points? That's going to be the integral from A to B of the square root of 1, just a constant, plus the derivative of the function y with respect to x squared. So we're taking the derivative, we're squaring it, and then remember we're square rooting that entire inside, and then we add this dx on here, just saying it's with respect to x. But if we could call this like this part here, maybe like dy by dr squared dr, right? It doesn't really matter what the variable is as long as you're consistent. So this is the formula. Now let's go about actually deriving how we get there, and then I'm going to show you how we can use that to find the circumference formula and how we can apply it to some different problems, okay? So let's just uh, go with some random curve here. Hold on. So let's say our curve looked like this, and it was here to here from A to B. What is this arc length going to be from A to B? This is some portion of our function. We're trying to figure out if we were to cut a string, how long would that string be to kind of attach those 2 points there. So if we zoom in here, right, all this really is we're taking the sum, I'll kind of go back here. We're taking the sum of an infinite number of super tiny strings, infinitely small and infinitely many of them, and we're just adding those up. So let's say we're looking at this string right here. Let's call this DL. To figure out, I'll just kind of blast this up over here. If this was the amount we changed in our length, that's going to correspond to how much we change in the x direction dx and how much we change in the y direction dy. So if these changes are infinitely small, we're going to get an infinitely small change in our length. And if we add up an infinite number of infinitely small changes in length, that's going to give us the net change in length in total of this entire curve from some interval. Okay, so if we're adding up an infinite number of those, let's just figure out what dl is going to be. Okay, so if this is dx, dy, we'll call this dl. So the change in L is going to correspond to a super small change in x, super small change in y. That's really what calculus is, right? Is just summing up infinitely many infinitely small changes in some quantity. So using our Pythagorean theorem that we already know, we know that dl, right, our change in L squared, that's going to be dx squared plus dy squared. Okay, and just solving for dl, all we have to do is square root this, because the square root of dl squared is just dl. So it's going to be the square root of dx squared plus dy squared. Right? Nothing too crazy so far. So the arc length, we know what the formula actually is, but what it's really doing is, we don't actually know the bounds yet, but I'll call it L. L is going to be the integral from a to b of dl. So this integral, lots of people get confused. They don't really know what it means. They think it means area. It doesn't always mean area. All like this integral sign, it's called an elongated S. So if you take an S and you stretch it out, that's really what an integral is, and that just means sum. So it means we're summing up from A to B an infinite number of dLs, and that's exactly what we were just talking about. If dl is this change in length, we're going to look at one change in length, which is right here. We're going to add this one and add this one and add this one and add this one. We're going to add up an infinite number of them, and that's going to give us our total arc length. So when we integrate from A to B, dl, that is going to give us our arc length. Okay, well, what is dl actually? Well, we just figured that out. We can figure that out in terms of x and y, or dx and dy. So instead of the integral from a to b of dl, I'm going to write the integral from a to b of the square root of, not x squared, dx squared plus dy squared, right? And notice how we do not have a dx here or a dy. So we can't just tack that on. We have to algebraically manipulate this thing to bring this dx on the outside, because our function up here, that's going to be a function of x. So when we write our integral, we want to somehow find a way to bring this dx on the outside. Okay, and what we can do is we can factor out that dx. So, excuse me, instead of writing what we just did, we can say the integral from a to b of, we can factor out dx squared, and what we're going to have left is 1, right? Because dx squared times 1 is just dx squared, plus dy squared over dx squared. So what this means is when we expand this dx squared into both these terms, we're going to get dx squared plus dy squared over dx squared times dx squared. And these dx squareds are going to cancel, and it's just going to be dx squared plus dy squared, which is exactly what we want, which is what we had before. Okay, so if we factor out that dx squared, notice how this is a product now. So anytime we're taking the square root of something, we can separate it only if it's a product or a quotient. Before, we couldn't just say the square root of dx squared plus dy squared was dx plus dy. That's not how square roots work. We can only separate them if they're products or quotients. So now, since it's a quotient, we can say it's the integral from a to b, right, of the square root of dx squared times the square root of 1 plus dy squared over dx squared. So the square root of dx squared is just dx, and I'll save that for right now, but let's think about what the square root of 1 plus dy squared over dx squared is. Well, since it's a sum right now, we can't really split it up, so it's going to be 1 plus dy squared over dx squared. Since both of those things are being squared, we can just call that dy over dx all squared because this squared applies to both of these numbers. So we can kind of not factor out, but bring out that square so it applies to both of them. And now we can tack on this times dx. So now this is looking like something we can integrate because we have our bounds a to b, and we have the derivative with respect to x of a function, and then we have our dx. So now that we have that dx on the end, we can actually, this is like something that we can integrate. And this is a direct derivation of what we started with. So just using our knowledge of calculus and what functions do when they change and how that can affect arc lengths, we can derive this equation, and this is going to relate back to what we have right here. It's the same thing, right? So if we were to have some function, right, looks like this, from a to b, we can figure out how long this is by figuring out what our function is, differentiating it to the first degree, so taking the first derivative of that function, plugging it into this equation. So it's going to be the square root of 1 plus the derivative of that function squared dx, and we're going to integrate that from a to b, and that's going to give us our arc length. Okay, so let's figure out how they got the circumference formula, c equals 2 pi r. Right, because we see this everywhere. If we have a circle, right, and we know that the radius is r, everyone says, oh, well, the radius of that is just going to be 2 pi r, and the area is pi r squared. And we can figure out the area just by integrating it. That's not like as difficult as this question here, where we want to find the arc length of the entire thing, right? We're not just finding the area, we're finding like what the actual length of this circle is. Okay, and in trigonometry, we know that our area, or our arc length, sorry, is going to be theta r, where theta is our angle in radians and r is our radius. But it's not that simple anymore because we're thinking of it in terms of r and not theta. Okay, so when we don't have theta and we just have r, it's going to be a little trickier. How can we figure out what that's going to be? Well, let's use the equation we just derived. So if we know that the integral from a to b of the square root of 1 plus dy by dx squared, dx is going to give us our arc length. Let's just think about what the function of a circle would even be if we were to graph it, right? So we want it to be a function of x. So if this is our x and this is our y, right? We can't actually graph a function if we're talking about a circle. So if we have a circle that looks like this, right? You might remember from like your younger grades when you were doing this that this isn't a function, because if we were to do the vertical line test, right? We had a vertical line and it traversed to the right across the circle, it would touch multiple points on the circle the entire way through. Like right here, it would touch it twice, right here, it would touch it twice, right here, it would touch it twice. So for any given x value, there are multiple y values that would correspond to that x, and that's not going to work out if we want to have a function. So what we're going to actually have to do is we're going to have to find the area, or sorry, the arc length. Let me just make the circle nicer here. The arc length of half a circle. So we'll call this negative r. Call this r, right? Because our radius is just from the origin to the outside. From negative r to r, and then we're going to have to double that. Because right now, this is a function. If we were to do the vertical line test, have the line traverse across the left to the right, it would only touch 1 point for any given x value, or r value, I guess. So I'm going to change this to r. So this is going to be a function of r now. Okay, so if we want to use the formula to figure out the circumference, let's just write out that formula. I'm going to write L. That's going to be the integral from negative r to r, right? That's what we just figured out, of the square root of 1 plus dy by dx. And then we can't say dr for this one because our bounds are in terms of r. So we're actually going to write dx. So we're going to integrate this with respect to x. right? So that's actually my bad. This should be your x. So r isn't your independent variable. It's just the bounds that we're going to use for this question. You could switch those, so you could call this negative x and call this r, but it doesn't really matter as long as you're consistent. So let's see here. What do we have to do? Well, we have to figure out what the derivative with respect to x is of our function y. So the equation for a circle is x squared plus y squared equals r squared. So x squared plus y squared equals the radius of that circle squared. Okay, so how can we get y on its own here? Well, y squared is going to be r squared minus x squared if we were to move this x over. Okay, so if we just want y, we just square root that. So y is the square root of r squared minus x squared. Okay, but we want dy by dx. We don't just want y, right? Because in our formula, there's nothing to do with just y. We want dy by dx. So let's differentiate this. dy by dx, since these two are equal, it's going to be d by dx of the square root of r squared minus x squared. Okay, well, what's that going to be? So when we're taking derivatives of square roots and functions with multiple things inside the square root, dy by dx, let's see here. Well, we can rewrite this as r squared minus x squared to the power of 1/2. So d by dx, right? Because square root, the index is 2, and the exponent on this is just 1. So if we raise this to the power of 1/2, that's an equivalent way to write it. So let's go a bit further here. Right? If we want to differentiate this, we can just use our power rule. So we're going to bring the 1/2 out in front. So it's going to be 1/2 r squared minus x squared. And if you remember the chain rule, when we're differentiating something with powers, or even sine or composite functions, if we're differentiating them and the inside isn't just x, it's like it's a power of x, or there's something else in there, we have to multiply by the derivative of the inside. So r squared, remember, that's just the radius of our circle squared. So that's just a constant. So we're going to have a constant minus x squared. So the derivative of that, that's just going to be the derivative of r squared, which is 0, right? Derivative of a constant, minus the derivative of x squared. And that's going to be negative 2x via the power rule. We're going to bring that 2 out in front, lower the exponent by 1. So that's going to be times negative 2x. Now let's just simplify this a bit. Okay, we have 1/2, and then we have that multiplying into negative 2x. So those 2's are going to cancel. We're just going to have negative 1x or just negative x, right? And I forgot to add an exponent here. When we had that 1/2 and brought it out in the front because of the power rule, we had to lower the exponent on this by 1. So 1/2 minus 1, or 0.5 minus 1, that's just negative 0.5, or negative a half. So let me just simplify this here. We had negative x because these 2's canceled. And r squared minus x squared to the negative a half, that's just 1 over r squared minus x squared to the positive 1/2, right? If we reciprocate this term here, we can make that exponent positive. So it's going to be negative x over r squared minus x squared to the power of 1/2, or the square root of r squared minus x squared. So we're seeing that square root of r squared minus x squared come back, except it's on the bottom now. And it's going to be multiplied by negative x on the top. Okay, so this is our dy by dx. Now that we have dy by dx, we can just plug that in to our formula for arc length that we just derived. So the arc length of the circle, L, that's going to be the integral from, or not r, negative r to positive r times the square root of 1 plus dy by dx. I'm sure you're getting tired of me writing this, but now that we know dy by dx, we can just plug that in. So 1 plus dy by dx, that's negative x over the square root of r squared minus x squared. Okay, so negative x over, and this is actually squared. I keep forgetting to write all this stuff. It's been too long. I'm just getting over COVID and I haven't done one of these videos in a while, so bear with me here. Over the square root of r squared minus x squared, quantity squared with respect to x, so dx. We're summing up all of these square roots from negative r to r with respect to x. Okay? So now, let's apply this square into both these numbers. This is going to work out nicely because we had a square root on the bottom, and if we're squaring a square root, we're just going to be left with what's on the inside. So it's going to be 1 plus negative x squared. That's just positive x squared, right? If we're squaring negative x times negative x, the negative goes away. We just get positive x squared. And the bottom's just going to be r squared minus x squared, right? Because we're square rooting, or we're squaring that square root. So that's going to go away, and then we got to add our dx here. Okay, good. So let's combine these fractions now. So we have 1 plus x squared over r squared minus x squared. We can just write 1. Okay, we can just write 1 as r squared minus x squared over r squared minus x squared. Because if you have something and you divide it by itself, that's always going to give you 1, right? If you had 500 over 500, that's going to give you 1. If you had 3 over 3, that's going to give you 1. If you have x over x, that's going to give you 1. So r squared minus x squared over r squared minus x squared, that's also going to give you 1. So we're going to have r squared minus x squared dx. Okay. So now dx r squared, we can, since these denominators are the same now, we can go r squared minus x squared plus x squared, right? We're just summing up all the numerators in the top there, divided by r squared minus x squared. Okay, so we're just going to keep simplifying this, a lot of simplifying. R squared minus x squared plus x squared. If we have negative x squared and we're adding x squared, we're just going to get what's left on the left there. So r squared, the x squared is going to go away, over r squared minus x squared. Okay, so what we have now is negative r to r. Okay, so if we're square rooting this quotient, and I forgot my dx there, if we're square rooting this quotient, that square root's going to apply to the r squared and to the r squared minus x squared. So let's just square root both of the top and the bottom. The square root of r squared, that's just going to be r. Okay, and we don't need to worry about the plus and minus because the square root was already there. Okay, and then we're going to have over the square root of r squared minus x squared dx. Okay, well, you'll remember if we have r over some number, r squared minus x squared square rooted, r is just a constant, right? So this is like 5 over something or 10 over something. Anytime we have a constant that we're multiplying inside the integral, we can just factor that out of the integral completely. So it's going to be negative r to r, right? Now the inside is going to be 1 over the square root of r squared minus x squared dx. Okay, so now we're basically done simplifying this. All we have to do now is look at our integration table. So we found earlier that if we had the definite or indefinite integral of 1 over the square root of a constant squared minus our variable x squared, that's going to be, obviously we have our r here, but it's going to be r. This integral is what we're looking at. So the integral of 1 over the square root of a constant squared minus x squared dx, that's going to be arc sine, or the inverse sine. Not sure what notation you're familiar with, but of our variable x divided by whatever that constant is. So our constant in this case is r. We're keeping it general. So it's going to be arc sine of x over r, okay, evaluated from negative r to r. So we've gotten rid of this integral entirely. We integrated 1 over the square root of r squared minus x squared dx. Got it in terms of just numbers and variables with no integration. So we have r. Let's evaluate this. So what these bounds are saying is we're evaluating this expression here, and we're just plugging in r and negative r where we see x. So it's going to be the arc sine, right, of r over r minus the arc sine of negative r over r. That's all integration is doing. Once we integrate it, we have to evaluate it from our bounds. And our bounds from the integral were negative r and r. So we're just plugging that in where we see x. And this is what we're left with. Okay, well, even though we don't know what r is, it doesn't matter because r over r, like I was just talking about, anything over itself is 1. So this is just r, and instead of arc sine, I'm just going to write sine to the negative 1. That's just a notation I like using. Inverse sine of 1 minus the inverse sine of negative 1. Okay, well, sine of pi over 2, that's 1. So that must mean the inverse sine of 1 is pi over 2. So if we take the inverse sine of 1, we're just going to get the inside of this. That's what the inverse sine is really doing. It's kind of going backwards. So this is going to be r times pi over 2 minus, well, the inverse sine of negative 1, that's just negative pi over 2, right? Because we're just tacking on that negative. So it's going to be negative pi over 2. And anytime we subtract the negative, that just means we're adding a positive. So pi over 2 plus pi over 2, if you have half of something and you add a half of another of that thing, you just get one full of those things. So it's going to be half of pi plus half of pi. That's going to be a whole pi. I feel like having a whole pie right now. So that's just going to be r pi. Hold on, I thought you said that the circumference was 2 pi r, right? This is just pi r, if we flip those orders there. So we found that it was pi r, but I thought the circumference was 2 pi r. Well, remember when we started, we said we can only integrate functions with what we were doing. If we were to integrate the entire circle, that wouldn't be a function. So we found the arc length from negative r to r of the function of a semicircle, right? We're saying that this area is pi r, but if we want the area, or the arc length, sorry, of the whole thing, let me just make this a little neater. That's going to be just twice of the upper half of that circle. So the entire circle circumference is going to be times 2. So that's going to give us C, or L, equals 2 pi r. So that was a lengthy derivation, I know, but that's how we get our circumference formula. I know some people, they go through trigonometry and say, well, A equals theta r. That's all you really have to know about arc length. But that's only when we're dealing with circles. With this function here, this is so cool. No matter what the function is, we can differentiate it, square it, add it to 1, square root that, and then integrate it from a to b with respect to x, or whatever your independent variable is, and we're going to get our arc length back. No matter if it's a circle or a cubic or a sine function or a tangent function or an exponential or a logarithm, whatever it is, we can apply this formula and figure out what the arc length is without having to know that it's a perfect circle and without having to know the angle, right? So let's say we were dealing with y equals x cubed, right? Y equals x cubed looks something like this. That was an absolutely terrible drawing. So I'm just going to redraw this because I have terrible OCD when it comes to doing this stuff. Okay, so y equals x cubed looks something like that. let's say we want to find the area, or sorry, the arc length. What am I saying? 0, and let's call this A. So we're trying to figure out the arc length from 0 to A of y equals x cubed. Well, we just use our formula. We know that R or L is going to be the integral, our bounds, right, are 0 to A. That's what we're looking at. So if we were to cut a string and lay it across the plane from 0 to A, how long would that string have to be? So that's going to be the square root of 1 plus dy by dx squared dx. Okay, well, our function y, that was just y equals x cubed, right? They specified that in the question. So we're going to have to differentiate that, find dy by dx. That's just going to be 3x squared. So from 0 to A, square root of 1 plus 3x, or I guess I can write it, 3x squared dx. So that's going to be integral from 0 to A, square root of 1 plus 9x to the fourth times dx. Okay, so this video, I'm not going to go over like how to integrate something like this. That's not really the purpose of this video. But there's techniques that we can do to integrate this without a ton of difficulty. We can evaluate that from 0 to A, and we will get the arc length, how long that string is going to have to be to lay across the plane from 0 to A. So I think that's pretty cool, and I hope that this derivation made sense, and I hope I explained how we can apply it and put it to good use, and I'll see you in my next video.